This is a talk for the International Colloquium on Automata Languages and Programming, also known as ICALP 2020. I am Zihan from University of Chicago, and in this talk, I'm going to present my paper with Julia Chuzhoy and Merav. The title of our paper is Unpacking Low-Diameter Spanning Trees. So I'd like to motivate the problem of packing low-diameter spanning trees with an example, the multi-message broadcast problem. In this problem, we are given a network and a special node. And the special node wants to broadcast n messages in the network. The message propagation in the network proceeds in synchronous rounds. In each round, only a single message can be sent through an edge. So how should we organize the message transmission in each round so that the broadcast can be done in a small number of rounds? It was shown in previous work that there exists a simple forwarding strategy where in each round, each node forwards a new message to its neighbors through its incident edges. And it was proved that by properly arranging the order of forwarding, it takes about the diameter of the network plus n rounds to broadcast n messages. And this bound is optimal in general, for example, when the network is a pass. So how does this high edge connectivity help in this problem? Or to put it in another way, if the graph has high edge connectivity, can we design a better protocol to broadcast n messages in fewer rounds? Since intuitively in the graph is well connected, then a message can be spread very fast. So as shown in this slide, if we can find two edge disjoint spanning trees in this graph, then we can simply distribute the task of n message broadcasting into n/2 message broadcasting tasks, basically two smaller tasks, and let the first spanning tree take care of the first task and the second spanning tree take care of the second task. Since two trees do not share an edge, the two tasks can be done in parallel. In particular, if we denote by D1 the diameter of the first tree and D2 the diameter of the second tree, then we can broadcast n messages in the maximum of D1 and D2 plus n/2 rounds. So this motivates the notion of tree packing. As shown by this example, one way of making use of the high edge connectivity of the graph is to compute a packing of spanning trees in it, and then distribute the task on these trees. So a spanning tree packing is simply a set of spanning trees in a given graph. And we will be focusing on the following three measures of a tree packing. First, the size of a spanning tree packing is defined to be the number of spanning trees in this set. Second, the diameter of the spanning tree packing is defined to be the maximum diameter of all trees in this set. And third, the congestion of a spanning tree packing is defined to be the maximum appearance of an edge in these trees. Namely, a tree packing has congestion C if an edge in the original graph appears in at most C trees. Clearly, as shown by the motivating example, these three measures are the main factors that determine the round complexity of a problem. So now we're going to review some previous work on spanning tree packing in a graph. The celebrated tree packing theorem of Tutt and Nash-Williams theorems from 1961 states that every k-edge connected graph contains k/2 edge disjoint spanning trees. And in other words, a k-edge connected graph contains a packing of spanning trees with size k/2, congestion 1, and probably n-bounded diameter. This beautiful theorem has numerous algorithmic applications, but unfortunately, it provides no guarantee on the diameter of the individual trees in the packing. And in the worst case, the spanning trees may have diameter as large as n, even if the diameter of the original graph is very small. Another celebrated graph theoretical theorem on k-edge connected graph is the Karger's edge sampling theorem. It says that for every k-edge connected graph G, the graph G log n over k, which is a random subgraph obtained by sampling each edge of G independently with probability log n over k, is connected with high probability. So here we have k to be at least log n. And this theorem also has the same problem, which is that it says nothing about the diameter of the random graph obtained by edge sampling. So for now, it is still unclear how to compute a tree packing whose diameter is sublinear in the number of vertices in the graph, even if the input graph has small diameter. And all we have is a negative result shown by Ghaffari et al. In 2013. They show that for any k larger than log n, there exists an inverse k-edge connected graph of diameter d, which is log n, such that in any partitioning of the graph into spanning subgraphs, all but log n of the subgraphs have diameter at least n over k. So this result leaves an open problem on what we can say about the case where the original graph G has diameter smaller than log n. And in this paper, we make progress towards both the algorithms and the lower bounds for computing a packing of low diameter spanning tree. So our result can be summarized in the table, and we have omitted polylogarithmic factors for the simplicity of presentation. And our results in this table are algorithmic. The first row restates the Tutt and Nash-Williams theorem, which says that every k-edge connected graph contains k/2 edge destroying spanning trees, but the diameter can be unbounded. Our first result shows that every k-edge connected graph with diameter d contains a packing of size k over log n, congestion 1, and diameter at most k to the d squared over 2. So when d is small and k is not very large, this gives good bounds on the diameter. And in fact, the algorithm for this result is exactly the Karger's edge sampling algorithm. So this result can be seen as a strengthening of Karger's theorem. Our second result shows that every k-edge connected graph with diameter d contains a spanning tree packing of size k over 2, congestion 2, and diameter at most k to the d. Note that this is an exponential improvement of the diameter compared with the edge disjoint case, which is kind of common in many graph theoretic problems. So you may wonder, what if we allow a little more congestion, for example, 3 or 4 or maybe larger constants? Can we get another exponential improvement on the diameter from the congestion 2 case? And the answer is no. Our third result shows that for any kd alpha mu, there exists a k-edge connected graph with diameter d, such that in any connection of k over alpha spanning trees that causes congestion as multi mu, there must be one tree that has diameter at least omega k over alpha d mu to the d. So in this case, from the previous result, from the second result, we can immediately obtain an upper bound of OK over alpha mu to the d, and which is by first obtaining k over alpha mu spanning trees of congestion 2, and by directly duplicating each tree, mu or 2 times, we get k over alpha spanning trees of congestion mu in total. So this lower bound basically says that when the diameter is small, we cannot do much better than scaling the congestion 2 case. And lastly, we studied the case where the graph is KD connected. Here we say that a graph is KD connected if for every pair of nodes there exists k-edge disjoint paths connecting them. Each has length at most d. Note that this is a stronger notion of connectedness. The reason that we study this case is because the high upper and lower bounds of the first three results do not seem very satisfying, and therefore we need to maybe strengthen the notion of connected. And here the notion of KD connectedness is a natural generalization and strengthening, since if a spanning tree packing of size k and diameter d exists, then the graph must be KD connected. And it will be interesting to know whether or not the opposite direction is also true. And what we proved is that every KD connected graph contains a collection of k spanning trees causing congestion log n and has diameter at most d log n. So now let's see some applications of our results of finding low diameter spanning tree packing. First, let's look at the motivating example at the beginning of this talk, where we want to broadcast n messages in the network. Now, if the graph is k-edge connected, then we can first compute a spanning tree packing and then distribute the task of broadcasting n messages into smaller tasks and let each spanning tree take care of one task. It can be shown that in this way, we can broadcast all messages in k to the d plus n over d rounds. So if k is large and d is small, this improves upon the previous d plus n rounds. Our algorithm of computing low diameter spanning tree packings have many applications in distributed computation. So first I need to briefly introduce the Congestion model, which is standard model in distributed computation. In this model, we are given a network that is modeled as a graph. And there's one processor on each node. And initially, each node only knows its instant edges. A distributed algorithm proceeds in synchronous rounds, and in each round, every node can send log n bits to each of its neighbors in the network. And eventually, each node has its own output. So the complexity measure of a distributed graph problem is the minimum number of rounds of communications that is needed to solve the problem. So first applications of our tree packing algorithm is that the algorithm gives improved round complexity for many central graph theoretic problems in k-edge connected graphs. For example, the computation of minimum spanning tree, a global minimum cut, or ST shortest path. And this is done via an improved construction of the structure of a low congestion shortcut, which is a basic communication backbone that is used in algorithm for several optimization problems in the Congestion model. The optimal round complexity for these central graph theoretic problems was theta d plus square root of n for general graphs. And with the improved construction for low congestion shortcut, we obtain improved round complexity for these problems in k-edge connected graphs, which is the minimum of square root of n over k plus d n to the d over 2d plus 1 and n over k. So note that if k is large and d is small, this improves upon the square root of n lower and upper bound for general graphs. Our second application is for constructing distributed algorithms that are resilient to edge failures. So we say that a distributed algorithm is resilient to an edge failure, or it is one resilient if in the presence of an adversary who can corrupt the message on one edge in each communication round, the algorithm still outputs the correct solution. So in previous work on resilient distributed algorithm, Parter et al. Proposed the notion of low congestion cycle cover, which is a similar structure as low congestion shortcut. And they show that with the construction of low congestion cycle cover, they can convert any non-secure distributed algorithm into an equivalent one resilient algorithm, while paying only a small overhead in the number of rounds. And our algorithm of tree packing can be used to generalize and improve the construction of low congestion cycle cover in k-edge connected graphs. And as a corollary, we can use this to convert any non-secure distributed algorithm to secure ones that are able to handle more than one, actually up to omega k edge failures. And there are many other applications in distributed algorithm. For example, we provide improved round complexity for information dissemination problem. And we also provide a distributed algorithm for approximate verification of edge connectivity. Another application that worth mentioning is that we provide the first separation between the round complexity of the minimum spanning tree computation and the approximate minimum global mean cut. In the distributed graph theory literature, the problems of approximating the global mean cut and the problem of computing a minimum spanning tree are considered to be more or less equivalent in terms of their round complexities. In fact, the classical algorithm for minimum cut are based on repeated computation of minimum spanning tree. And we show that this is no longer the case in the family of moderately high connected low diameter graphs. So we now begin to show some detail of our algorithm and lower bounds. We will mainly focus on the congestion 2 case and try to illustrate the main ideas and techniques. Recall that Theorem says that given any k-edge connected graph G of diameter D, we can efficiently compute a packing of spanning trees with size k over 2, diameter at most k to the D, and congestion at most 2. So our algorithm is pretty simple. Recall that the Tutt and Nash-Williams theorem already gives k over 2 edges to join spanning trees t prime 1 to t prime k over 2. But these trees may have large diameter. So how do we make this tree have small diameter? Well, we have to use the property that the original graph G has small diameter. The way we use this is by obtaining another BFS tree T of G. And then we use tree T to somehow fix the diameter of the trees t prime 1 to t prime k over 2. And the specific algorithm is that we let each edge of T uniformly random go to one tree of the set T'1 up to T'(k)(2). For example, these are the edges that decide to go to T'(I). And the union of this edge with T'(I) form a spanning subgraph G'(I). And what we do next is to run a BFS on each G'(I) to obtain the tree Ti, which is the resulting tree packing. So it's clear that we indeed find a collection of K/2 spanning trees, and it is not hard to see that the congestion of these spanning trees is at most 2. This is because the original set of spanning trees, T'(1) up to T'(k)(2) are edge disjoint, and together with T, they cause congestion at most 2. So every edge is used at most twice in the final packing of spanning trees. Now it remains to bound the diameter of each Ti. Since Ti is just the spanning tree of G'(I), it suffices to bound the diameter of G'(I). So we now analyze the diameter of G'(I). We begin with a baby version. Assume our base case, our base graph is simply a line of K log n nodes, and the BFS tree is just one node with an edge connecting these new nodes to every node in the base graph. So in this case, we show that with high probability, at least one green edge will stay. And we can let the corresponding nodes to be called selected nodes. So what if the base graph is a very long line that contains much more than K log n vertices? It's actually not hard to see that with high probability, at least one edge among these, among each consecutive K log n green edges will stay. Or equivalently, at least one node among each consecutive K log n nodes is selected. So as an important corollary, this implies that with high probability, the fixed graph has diameter at most K log n. So what about the case where the base graph is an arbitrary graph and the BFS tree is still consists of a new node and an edge connecting this node to each node in the base graph? We claim that in this case, with high probability, every node is within distance at most K log n from at least one selected node. So for example, these are the selected nodes, and we claim that they are dense. So this actually is not very hard to prove, but actually the analysis is just similar. It's just as similar as in the previous 2 baby version. So this finished the analysis for the case where the BFS tree has depth 1. And in fact, we're going to use induction on the depths of the BFS tree. So this serves as a base case. Now we show how induction works. The claim is that a random depth D tree can fix the diameter of a connected graph to K to the D. Here, a random depth D tree means that each edge of the depth D tree will stay with probability 1 over K and not stay with probability 1 minus 1 over K. So we consider a special case, which turned out to be the hardest case, that the base graph only consists of nodes on the bottom layer. So I show in this picture. So the base graph can be viewed as within the right circle. So we first sample all green edges that is incident to the base graph. So for example, these edges are the edges that decide to stay. So recall that in the base case of the induction, we have already proved that every node is within distance at most K log n from at least one selected node. So now we forget about all the other nodes and edges in the base graph and only care about the selected nodes. We construct another graph only on the selected node. Specifically, we add an edge between a pair of vertices in the pair of selected vertices if they are at distance at most 2 K log n from each other. And from the analysis of the base case, we can show that the graph constructed in this way is connected. Now we take nodes in the last but one level into account. So these are the nodes that are incident to the base graph, and we can discard all other nodes. And this is a new graph into account. So now the tree that are used to fix this has depths at most D minus 1. And we can use induction hypothesis and get that with high probability, the new graph is fixed to have diameter at most k to the d minus 1. And recall that each brown edge may represent a path of length k log n in the original base graph. We can eventually conclude that with high probability, the original base graph is fixed to have diameter at most k to the d. And this finishes the analysis in the congestion 2 case. So at the end of the presentation, I will briefly sketch the lower bounds of the result, which says that for any k alpha d mu, there exists a k-edge connected graph of diameter d, such that any packing of spanning trees with size at least k over alpha and the congestion at most mu must contain a tree with diameter at least k over alpha d mu to d. So the hard example is simply the union of a complete T-array tree with a carefully chosen T and k copies of a path of the post-order traversal of this complete tree, which is shown in red. So in the picture, every red edge in fact represents k parallel edges. So this graph has small diameter since it contains a complete tree. And it is not hard to see that this graph is k-edge connected since it contains k-edge disjoint spanning paths, which are simply the post-order traversal paths. And the argument is that if it contains many edge disjoint low diameter spanning trees, then it contains many edge disjoint short paths that go from the left bottom node to the right bottom node. But if you want to go quickly from the left bottom node to the right bottom node, then you have to go levels up and use the high level edges. However, there are not that many high level edges by design because it's only a complete T-array tree and the number of edges go levels up decrease significantly. So there has to be one path that slowly walk from along many red edges, and therefore this path cannot be very short. This creates lower bounds on the spanning tree packing, on the maximum diameter of the trees in the spanning tree packing. So to summarize, in this paper, we provide the first non-trivial algorithms and lower bounds on the diameter of spanning tree packing. And this gives improved construction for building blocks of many distributed algorithms, and in turn, proved improved round complexity for various distributed problems in high connected graphs. For some future directions, for the case of KD connected graph, we only get a result where the congestion is allowed to be logged in. So what about lower congestion, for example, constant congestion, or even edge disjoint paths is unclear. And in this paper, we only consider the K-edge connected graph. So what about other special families of graphs? That's probably also interesting problems to work out. And that's all. Thank you for listening.